Okay, in this video, I'm going to teach you how a half bridge inverter works. We're also going to build one. We're going to build one on this surface mount to through-hole pin adapter. I was reading through the data sheets of the gate driver, and it told me to keep the bootstrap capacitor as close to the pins as physically possible, which got me thinking that I can't use traditional breadboards, and I can't even use, solderless boards because they have quite long connections, and they can introduce parasitic capacitance and inductance and all that sort of nasty stuff. So I thought, if I just use one of these are really tiny, and I can just do like sort of flying wire on top of the gate driver to try and keep everything as tight as humanly possible. So I'm going to roll the fabrication of it. Okay, so before we build this thing, I really want to run through how it works with you. Okay, so just remember, the most important part is this loop right there, the bootstrap loop. So let's run through an example. We have 24 volts in 12 volts VCC. Okay, so what's going to happen? We start with the low side switch connected. Okay, this is going to pull HS to 0 volts, to ground, because what's going to happen is it's going to be pulled to ground. Okay, so the consequence of that is that when the low side switch is on, we have 0 volts on the bottom plate of that bootstrap capacitor. Okay, but on the top plate of the bootstrap capacitor, we have 12 volts. Okay, because 12 volts is coming in, right? It's charging that top plate, but the bottom plate is just getting slammed to ground. Okay, so that can't charge up. So we have a voltage difference across our capacitor. Okay, that's really important. So now, according to how this works, this driver specifically, so HB is connected to the gate, okay, and the source is connected to HS, okay. That's how it works. So when we go to turn the high side switch on, we have that gate to source voltage of 12 volts. So it can turn on. So we have a gate to source voltage, V equal to 12 volts. So the MOSFET can turn on, okay? So now, here's again the magic part, okay? We have that voltage difference. The high side switch turns on, okay? And voltage starts to flood in, okay? And then it starts to raise the HS node, right, from 0 volts, and now it's going to race up to 24 volts. Here's the part that confuses most people, okay? The capacitor doesn't like to have its voltage changed, right? Its charge changed. So what it's going to do is it's going to keep that same charge, but lift both plates, okay? So it does sound confusing, and it was confusing the first time I heard it, but the bottom plate is then going to go to 24 volts, and the top plate will go to 36 volts, okay? It's going to keep that 12 volts difference. There's a lot going on there, but we're not going to go into that right now. All you have to know is that now we have 36 volts at the HB node. All you have to know really is that it works, okay? So we have 36 volts at the HB node. That means that when that 24 volts races in, and now the source is at 24 volts, that bootstrap capacitor has, now HB is at 36 volts. So now we still have that 12 volt difference to keep that high side gate open. Now, the thing with a half bridge inverter is it sort of cheats its way, right? So you've heard people say you get half the input voltage, and that's true. Now, the reason that is because these two capacitors provide a midpoint, okay? So we have 24 volts here, and at this midpoint here, you're roughly going to get 12 volts, okay? So what happens is that when we get the high side, let me just get rid of this stuff for now. when we have the high side switch on, the current flows like this. It goes through the MOSFET, right? You know, charges that, but there's really no current path going this way because I hit that diode straight away. So then it will go through the load, okay? And it will go to the capacitor ground, right? And it's, you know, it's gonna push charge to the ground, but it sort of goes to the capacitor, okay? And that's at 12 volts. Now, now when it goes the other way, right, so the low side switch is on. Now what happens? Well, the 12 volts, these capacitors store charge, right? So it's going to, so the capacitors store charge from V in, right? And so they're gonna supply that charge to send current back the other way, right? Sort of like a battery. But that node is at 12 volts. So it's gonna send voltage the other way. And if you do that difference, right, you know, 24 minus 12, you get 12 volts. So you're really getting 12 volts across that load. 12 volts back and 12 volts back. So you get a 12 volt alternating wave. And that's basically how this is gonna work. Now you might be wondering what all the other stuff is on the circuit, and that is completely normal to ask. So we'll just go through that, hopefully really, really fast. We have obviously our controller, which is going to do a PWM signal. Now on the STM32, you have something that's called a complementary. So it's embedded in the software, in the chip, and it will generate the complementary of a PWM signal you generate on a certain channel. VSS is ground, and that is connected to the low side output. And basically you have low output, high output, and then you have the HS, which is connected to the bootstrap, and then you have VDD, which actually powers the chip. And then yeah, you have gate resistance, and then the two capacitors right there that are going to supply you the voltage that you need. Yeah, so these capacitors are there to provide a midpoint, because if these capacitors have to be equal voltage, right? If they're not equal, you create an uneven, it won't be 12 volts here. And they also provide the voltage required to power the low side and the current, because their position is so close, they provide that current draw that the MOSFETs need for switching. And so yeah, let's start building this thing and see how we go. So after the longest time of trying to solder flying wires together, it burns out. And the reason it burnt out was because I accidentally created a short straight to ground by not adding any capacitors on the right leg. Put the diagram up here. And so at this point I thought, you know what? I'm done with making wire fly across the air on this tiny little surface mount to through-hole adapter, and I got straight away designing a PCB. So I thought I'd give you some quick tips on how to build a PCB, especially this one because it has some helpful tips in the data sheet. So here's the schematic here, and that's all fine. But if we go to the data sheet, you can see in the yellow, it recommends having the bootstrap capacitor as close to HB and HS pins as possible. So that's HB pin and HS pin. So if we go over to the inverter, you can see that this is my capacitor and it is as physically close to those pins as possible. I couldn't put it any closer. But not only the capacitor, but the whole power circuit. So you can see from V in to these capacitor banks here and here, they have to be really close to the load. They can't be situated, you know, far to the right, or this one far to the right. So they have to be as close as possible. Same with the switches. This loop right here is this part here. So this node here, that's the middle part. So that's got to be kept as small as possible. And you notice, add thicker wires for the power loop because we're going to have some current going through that. For the other side, you can add the thin wires, it doesn't really matter, but for the power loop, have some thick wires. And then what else? That should be all for now. And then it came 3 days later, and this is what it looks like. So I'm so pumped with how this turned out. Every component fit because Easy EDA has a mad library where you can select all your components and it gets the sizing just right. And this looks production ready, bar the testing tabs I soldered on there, but it looks really good. So we're going to test it. Now we're going to hook it up to the oscilloscope and the power supply and we're going to test it. All right, nothing's smoking out, so that's good. So we're going to start measuring. So fingers crossed. You won't believe this, it so works, and I'm going to show it to you. So this is the PCB that we made, right? So we got sent off, and the reason it's working is because everything is so nice and spaced out, and it's just such a relief. Let me show you. The oscilloscope. All right, let's have a look here. All right, that pink is what we want to see. And we have on the A cursor, 4 volts, and then negative 4.7 volts. So that means we have, and our power supply is 8.8 volt. So that's just doing the math. I've just got 2 probes hooked up across the load, and I'm just minusing them from each other, almost like a differential probe. And we have a 8.8 volt AC wave. I just cannot believe how good that turned out. And it's super crisp, super clean, very little noise as well. Okay, and there you have it. We have finished the half bridge inverter and it works flawlessly. Now you might be thinking like, you know, it's a really small AC wave. What can I really do with it? In the next video, I will be buying a tiny speaker and we can play some music with this by programming certain frequencies on the board to play on here. We can change the switching frequency to adjust the frequency of the speaker, and that can make music. Or you can put an LED, which I don't really want to do at 20 kilohertz, you're not going to see much or hear much at that frequency. That's like ultrasonic, but we can, you know, tune down to audible range. But I think a speaker is the best way. And then so after this, the next natural progression would sort of be a full bridge inverter with 4, but that's still a single phase inverter, but you'll get the full voltage instead of just half the voltage. And then the next step from that will be the 6-step inverter. But single phase are really, really useful because they can produce something that's super exciting to me, which is they can make induction furnaces possible. And if we scale a full bridge inverter up, I'm really excited to see what that can do. So stay tuned.